Right, we were discussing about dynamics of simple harmonic motion in the last lecture, and we had just about started with spring mass systems, looking at simple single spring type of system in both the horizontal situation and the vertical situation. So we'll take it from that point onwards today. Let's begin. So now we'll see some variations of the simpler system that we had started with in SHM of spring mass systems. So we'll see situations in which we can incorporate various things like not just a little bit of advanced application of Newton's laws and free body diagrams, but even applications of things like constraint relations and combination of springs and all that. So anyhow, let's begin with an example where we'll look at a variation of the vertical system, wherein we have a smooth inclined plane. So this is at an angle theta, and this is a smooth surface. And we have a single block attached via a spring, which is on the other side attached to a rigid wall. The spring has constant K. So let's say given to us that mass of the block is maybe 6 kilograms and angle theta is 30 degrees. Take G as 10 meters per second square. And the spring constant is, let us say, 12 newtons per centimeter. So now what is happening is that the block is initially held at rest in a position such that the spring is compressed by half a centimeter and released from rest. So show that it performs SHM, find time period, amplitude, and equation of SHM. Okay. And also find the maximum extension of the spring and the maximum acceleration and maximum velocity of the block during this SHM. Okay. So just go through the question and interpret it correctly first. Then we'll discuss about how to solve this. Okay. We will not solve this using work energy method or by free body diagram and then deriving the whole equation of SHM and all that. That is not required. We will just show that it satisfies the condition of SHM. And once we've got that, we will relate the problem with the standard equation of SHM and just find out things like amplitude, phase constant and all that by using the techniques that we discussed in the last lecture. That the value of omega comes from the physical properties of the system, whereas the value of amplitude and phase constant comes from the initial condition. So the initial condition is given to us in the language of the question. So you have to pay attention to that and you have to understand that which information will give you which of the parameters of SHM. Okay, so first thing you do is to show that it's an SHM. You try to show that there is a stable equilibrium position, and when we displace it from the stable equilibrium position, it will satisfy the condition that restorative force is proportional to displacement. If you're able to show that, then the first part is done, that you prove that it's an SHM. And from that equation itself, you'll get the value of omega square. So you'll know the time period. Because whatever force is proportional to displacement from mean position, The proportionality will give you the value of omega. Okay, so let's understand the starting point for this problem. In any general system of SHM, unless you are solving it by the work energy method, which we'll discuss after some time, you'll always start by understanding what is your equilibrium position. Because after all, you have to take that as the origin of your SHM parameter. So you must understand what is your equilibrium position. So if this is our equilibrium point, then acceleration at this point must be 0. So the spring must be having some amount of extension. Let's call that x naught at the equilibrium position. Okay. And that must be such that it's balancing mg sine theta, so that the block is in equilibrium. So at equilibrium position, mg sine theta is equal to kx naught. So the extension of the spring x naught is, just calculate in a moment how much it is. So the weight was, I think, 60, sine theta is half, and k was 12 newtons per centimeter. So x naught will come in centimeters to be 2.5 centimeters. Now also this equilibrium position should be taken as our, now I'll take the displacement from mean position as S. Okay. So this is our mean position. So now from here you can see that if we take the block to a position where it is above this point by displacement S, okay, or we take it to a position where it is below this point by displacement S like this, Either case, there will be acceleration which is opposite to the displacement. In both the cases, you will see there is acceleration. Okay, because in both the cases, the spring force will change. Here, the spring force will become kx, which will become k into x naught minus s. Okay, and here the spring force would have increased, become kx, where k is where x is x naught plus s. So whether you're going with the first diagram or the second diagram, both cases, you will get the relation that the first one, mg sine theta minus kx is equal to ma. So we will get ma is equal to k into s, where s is the displacement from mean position. And a you can see is minus d2s by dt square. In second case, you'll write kx minus mg sine theta is equal to ma. That will be the same result. And so not only your equation of SHM is there, but your omega square is the same value like a horizontal spring mass system or a vertical spring mass system. The angle of inclination theta makes no difference to it. What it makes a difference is to the position of the equilibrium. It is at an extension of the spring of 2.5 centimeters. Whereas in a vertical case, it would have been mg by k, so it would have been 5 centimeters, and in a horizontal case, it would have been x equal to 0. That's the only difference. Okay. This is the equilibrium. So hope this equation is clear to all of you. Either side of equilibrium at displacement of s results in an acceleration which is like this. So omega square of the SHM. So this shows that it's SHM with omega square equal to k by m. So time period equal to so numerically here that will work out to be taking the mass to be 6 kgs and the spring constant is 12 newtons per centimeter. So when you convert, so this is root 2 times pi by 10 seconds, approximately 1.41 into 0.31 seconds. That will become the time period. So this answers the first part, that you are showing that it's an SHM and you are calculating the time period. In fact, time period is in the second part. Yeah, so in the case 2, Vineet, see what is happening in case 2 is that your spring force exceeds mg sine theta, na? So the acceleration is in the above direction. So kx minus mg sine theta is equal to ma. Okay, and you substitute the value of x as x naught plus x naught. On the left hand side, what we are left with, we are just left with ks is equal to ma, and a is opposite in direction to s, so it is minus of d2s by dt square. Okay, using this equation, of course, that kx naught is equal to this equation. We are substituting that over here. Substitute this in this equation and again in this equation, and substitute the value of x in this equation as x naught minus s, and in this equation x naught plus s. Okay, very good. Okay, so that gives us, okay, now remember, once you've got time period, okay, then the rest of the things, amplitude and phase constant, will not depend on the dynamics. It will depend on the initial condition. So s is equal to some amplitude into sine omega t plus phi, where omega's value we know is root k by m, which was whatever. Root k by m would have been how much? 10 root 2 radians per second. Okay. But what about the value of amplitude and phase constant? So these will come from the initial state. That is, from here we can see that S's initial value is A sine phi, and V's initial value is A omega cos phi. So from that we know that the amplitude would be root of initial displacement square plus B naught square by omega square, and the phase constant should be tan inverse of S naught divided by V naught by omega. This kind of thing. Okay. So now see what is the condition given to us initially. Initially, the spring is actually compressed by 0.5 centimeters. So at t equal to 0, the block is being released from rest, but with the spring at a state of L minus x1, let's say, where x1 or x initial, where x initial was 0.5 centimeters. And compared to this, where is our equilibrium state? This is our equilibrium state. Okay, where this thing is such that this is L plus x naught, okay, where x naught is mg sine theta by k. So that is equal to how much it was? 2.5 centimeters. So the spring had an extension of this much. So what is our initial position with respect to mean position? It's this. This is our initial position. So at t equal to 0, you can see the position is equal to this. It is 3 centimeters away from the mean position, and the initial velocity is 0 because it's released from rest. So substitute this information here, and you get the amplitude as 3 centimeters and the phase constant as pi by 2. Okay. So my SHM equation is becoming like this, that S is equal to 3 sine omega t plus pi by 2, or S is equal to A cos omega t, where the amplitude is 3 centimeters and omega is 10 root 2 radians per second, or time period is so this is my equation of SHM. Now from this only we have to understand the maximum extension of the spring also. Okay. So in the question we have progressed up to this part now. We progressed up to here. Okay. We have shown that it performs SHM. We have found time period, amplitude, and the equation of SHM. Now what is remaining is this part. What is the maximum extension and also the maximum acceleration and maximum velocity of the block. So I'm just going to minimize this a little more so you can just go through this. So it's very important to understand the initial state from which we can understand the amplitude and the phase constant. So this part is very important. So amplitude and phase constant from initial state of the system. Okay, now you can see from this, anybody's got the answer for the maximum extension of the spring and the last part? How we'll figure that part out? See, you don't need to do any further calculation actually, really. You just need to understand the range of motion in the SHM. If this is our mean position, at this position, the extension of the spring was how much? 2.5 centimeters. And this was one extreme position. Okay, where this is one amplitude of 3 centimeters. So here the spring has a compression of 0.5 centimeters. But there's a compression, whereas this is an extension. So as the block goes from this side to the other side now, this is the other extreme. So it will be 3 centimeters below here now. So this is the other extreme. So at this position, what will be x of the spring? X of the spring will become 2.5 plus 3. That is 5.5 centimeters of extension. Okay. So this will be the position where the spring has maximum extension of 5.5 centimeters. And here it will have maximum compression actually. So it's never going above this of 0.5 centimeters. And that's why whatever acceleration it will have here, this is the maximum magnitude of acceleration. And you can see that there are two ways of calculating that maximum magnitude of acceleration. One is purely from SHM. It is A omega square. So it is 3 centimeters into K by M. So it is 3 centimeters into K was, remember, 12 newtons per centimeter divided by the mass was 6 kg by mistake. Okay. So the maximum acceleration according to this is coming out to be 6 meters per second square, Newton per kg. Or another way to calculate is that K into 5.5 centimeters minus mg sine theta is equal to m into this K max, as is mg sine theta plus K into 0.5 centimeters. Because at this position, the spring will be pushing it like this, Kx. Okay. And at this position, the spring will be pulling it back with Kx like this. So you can also verify the answer from these two, but it's totally not required. So here you can see this is 12 into 5.5 minus mg sine theta was 16 to half. So is equal to 6 into K maximum. So this should give us the same result. Yes. Just verify. Okay. So this will be newtons because K is in newtons per centimeter. 66 minus 30 is equal to 6 K max. So K max you can see is 6 meters per second. This will tell us that 30 plus 6, the maximum acceleration is this one. Okay. And the maximum speed, generally you would work out using work energy theorem, but here you can just use the SHM equation at mean position. The maximum speed of the block will be 3 centimeters multiplied with 10 root 2 radians per second. So that is 30 root 2 centimeters per second or 0.3 root 2 meters per second. Okay, so people hope this is clear. Okay, now we'll just look at some pretty ordinary type of questions which have combination of springs involved. In fact, we'll just finish off that combination of springs thing with one example. More than enough, I think. So we have this kind of a system, smooth floor and two rigid walls, and we have kept some kind of an object like a block over here. Now there is, let's say, this kind of situation. There are two springs connected like this, and then another two springs connected like this over here. So these are all having constants which are given. So at the given position, all springs are at their natural length. Now, given that K1 is, let us say, 4 Newton per centimeter, K2 is 2 Newtons per centimeter, K3 is 6 Newtons per centimeter, and K4 is 3 Newtons per centimeter. And the mass of the block is, let's say, 2 kilograms. The horizontal surface is smooth. Okay. The floor is smooth. Find the time period of oscillation for the block. If it is disturbed from the mean position, then how much time period it will have for the SHM? Just work this out quickly. This should not take too much time. Okay, just try out this question. Yes, very good, Aman. That's correct. Get the time period as pi, I think. Okay. So see, the simple way of doing this question is that you start reducing it to an equivalent spring. No need to apply dynamics, no need to make free body diagram, don't do any of that. So just what you do is, first step, you see that these two are in series combination. Okay. So the equivalent spring constant will be, okay. So when you work that value out, you will see it as 2 newtons per centimeter. Okay. So now change this to an equivalent system where you have only one spring on this side. And that spring is, let's say, K prime, which is 2 Newton per centimeter. And these are your K1 and K2 as was given. Okay. Now you will see that these two are in parallel, and that's in parallel with this also. So this is a parallel combination. All these. Okay. So the equivalent spring constant will become the sum of all this. So K1 I think was 4, right? And K2 was 2. And this is also 2 newtons per centimeter, right? So that is the overall equivalent spring constant of the whole system. So now you can see that this is equivalent to a single spring system, which has equivalent spring constant 8 Newton per centimeter, and mass of the block is 2 kg. So time period will just become 2 pi under root m upon this equivalent spring constant, which with SI unit and all will come out to be pi by 10 now in seconds. Might have just forgotten to convert to by SI units. So it should be pi by 10. So people, hope this is clear to all of you. Yeah. Both Amans you forgot. Okay. So just be careful about the units when you're. Okay. Now the next level of question that we have is sometimes when we have an arrangement of springs where you cannot reduce it using series and parallel. Okay. So I hope all of you are clear with the series and parallel equivalent concept of springs. Okay. If you have series combination of springs, you use the formula that 1 upon K equivalent becomes 1 by K1 plus 1 by K2. So whatever number of springs are in series. This is the end point. Then a combination like this can be reduced to a single spring. Whatever is connected to that end can be connected. And parallel combination has the formula that K equivalent is equal to summation of K. So parallel combination can be of two types, like everything is connected literally in what looks like a parallel combination from one side. Okay. Or it can also be that thing that we discussed in the above question. Okay. So this is a parallel combination, for example, or even if two springs are attached on either side, but with a block in between, this is also a parallel combination. This and this are also in parallel. Okay, now the next type of question we'll see is the one which is slightly more tricky than this, where there's a combination of springs which is neither in series nor in parallel, and we have to work out some kind of constraint relation. Suppose we have a smallish object like a particle, more or less, okay, attached to one spring which is attached to a wall on this side, but there are two other springs which are attached like this, and they are attached to two fixed walls. So these two are having spring constant K0 and K0, let's say, and this is having a spring constant K1. This diagram is symmetrical. So this angle theta is equal to this angle theta. So if we take this as our x-axis, this as our y-axis. Okay. So the system lies on a smooth horizontal plane which you can take as your xy plane, such that when the particle is at the origin of the system that I've shown, okay, where the x and y axis are meeting, all springs are relaxed. Now, first of all, show that if the particle is given a small displacement along the x-axis, which is the symmetry axis, it will perform SHM. And secondly, given K0 is suppose 4 newtons per centimeter and theta is equal to 30 degrees, okay, and K1 is 2 newtons per centimeter, mass of the block is 1 kg. You want to find the time period of this SHM. So in this case, you can see you cannot really reduce the problem to a single spring directly using series and parallel combination. So what you have to do is, and secondly, there is an additional condition involved that you are giving a displacement which is not only along the x-axis, but it is a small displacement. So if it is a small displacement, somehow we have to incorporate that fact in the constraint relation that we develop to understand that if the displacement is delta x, then how much each spring is going to get deformed by. Okay, what is going to be the deformation of each of the three springs that are shown in terms of delta x, which is the small displacement given along the x-axis. So from that, you will have to understand what the relationship between the displacement and the restorative forces. Okay, and that relationship will give you the value of omega square. So it's really about that geometrical constraint over here. Just try to figure this out. I'll tell you a couple of methods of doing this. Okay, so if you are in the process of solving it, just go ahead. Okay, I'm just describing over here what kind of geometrical constraint we have to develop. Okay, so instead of drawing the springs, just draw three lines which represent them. This is theta, this is theta. Okay. Now the idea is, let's say this was the initial position of that mass. So this natural length was L, then this natural length was L naught, this was L naught, and whatever, this was L1. Okay, very good, Kevin. I will just verify your answer. Now, if this point is displaced here by a small amount delta x, okay, so delta x is small compared to L1 and L0. Okay, then what is happening? This thing is now getting compressed, but by how much? It's getting compressed by delta x exactly. But these two, they are doing something else. They are becoming extended like this. Just correct the diagram, but understand the idea. Because these two are fixed points, you know, where the springs are attached to the wall. So this one is becoming L naught plus some, let's say, delta x prime. And this is also becoming L naught plus delta x prime. So we need to understand that there is some kind of a relation. What is the constraint relation between delta x prime and delta x? That we need to understand. Because once we have done that, then we can see, okay, this particle will have an acceleration like this. And that acceleration will depend on the combination of the forces now. Because this spring will be pushing it with K1 delta x. Okay. But these two springs will be pulling back. I'll just give you the answer in this thing form. Your omega square will become K1 plus 2 K naught cos square theta divided by M. So Kevin, you can just verify if this is the thing you got. I'll check your answer numerically also. Now to develop this constraint, we have a couple of methods. Okay. So one method is that I'm just drawing a rough diagram again here. So in this diagram, what we do is we take this distance as x. So when it goes here, this changes by delta x. And you take this distance as L. So this has become L plus delta x prime. You take this distance as h, which is a fixed distance. So one method is you can develop this thing that x square plus h square is equal to L square, where h is fixed, but x is changing to x plus delta x, and L is changing to, and this is changing to L plus delta x prime. Okay. And this angle is theta. So you can differentiate this relation. So if you differentiate this, or just apply the small change concept only, that's also fine. So this is like a very traditional way of solving the constraint relation. So it will become 2x dx by dt plus 0 because h is constant is 2l dl by dt. You can see the relation between these two is like this. So because delta x is small, we can take dx to be equal to delta x. Okay, and then dl will become delta x prime. So this is this total length here is length x plus dx. That is here. So that relation will go like this. So delta x prime will be delta x into x by L, or in terms of this theta, you can see that delta x prime will be delta x cos theta. So this is a constraint relation. And once you got the constraint relation, the rest is about free body diagram solving. So when you solve this FBD, you will see you'll get this value of omega square from this. Yeah, so vector addition to anyway you have to do, but you have to understand that just before you do the vector addition, delta x prime is not the same as delta x. Okay. That's why there's a factor of cos square theta, not just cos theta. One cos theta comes from the component part in the vector addition, but the other actually comes from the fact that delta x prime is not equal to delta x. It is a component of delta x. It is delta x cos theta. Okay, so hope the working out of the constraint relation is clear now. Now, next thing what we do here is solve the free body diagram. Okay, so back to that. So you can see that there are two spring forces which are acting symmetrically like this. Okay. K naught delta x prime and K naught delta x prime, and one spring force which is, if you take it to the opposite direction, it will be that all the forces will become opposite. So still it's the same thing. K1 delta x. So the acceleration that this block will have opposite to its displacement. But only the displacement is now a small displacement, so we'll write it as a delta x. So you'll see that 2 k naught delta x prime cos theta, because these angles are theta. So the angles are also the same. So this should be equal to ma. So add the third force. This should be equal to ma. So this is our first equation. This is our second equation. Now we introduce the constraint relation in the second equation. Substitute that here. So that's how we get that ma is equal to 2 k naught cos square theta plus k1. And a is actually minus of delta x. So instead of x, you have delta x because it's a small displacement. And that k equivalent is, yes, okay. So that will become how much now? Theta was 30 degrees, k naught was 4, and k1 was 2. And the mass of the block are taken as 1 kg. So my omega will come out to be okay. So the constraint relation in a problem like this becomes a little tricky, as you can see. So if anybody has a doubt with the constraint relation, please let me know. As I discussed, I'll give another method of understanding it also, but this is the fundamental method. Okay, now the second method for the constraint relation is much easier.
So
It is
above you have
the,
written is equal to.
sorry, come again, Rita?
Can you scroll up? Can you scroll up?
Yeah.
They have written MA is equal to 2k naught cos square plus k1. So delta x should also come up.
Yeah, sorry. There's in bracket here, there should be. No, that's your K equivalent. Where I've written delta x. This one, no? Yeah.
Yeah, sir.
So this is, yeah, this. Okay, so this part is done now. You understood. Okay, now let's take another approach for the constraint relation. By approach and separation velocity concept. So the same situation. Be very symmetrical actually. Anyway, so now what we do is we'll name these 3 points, these fixed points, and we'll consider as if P is moving towards one direction. So in this case, I'm naming them A, B, and C. Now suppose at the given instant, instead of actually displacing, I've just given this a velocity. P is given a velocity in this direction. So what is happening? P's approach velocity towards the point C is how much? It is V. Okay. But P's separation velocity with respect to the point A and P's separation velocity with respect to the point B, they are both how much? They are the component of that P, which is in this direction. They are the cos theta component. This angle is equal to this angle theta. So the separation velocity of P with respect to the point A is equal to the separation velocity of P with respect to the point B, and that is equal to how much? V cos theta. So in a time delta t, in a small time delta t, okay, the distance PC will reduce by delta x equal to V delta t because of this approach velocity. But in that same time, the distance AP or BP will increase by, let's say, delta x prime. Now that will be equal to how much? It will be V cos theta into delta t in a small time, because that theta should not be changing appreciably. So separation is happening. So you can see that delta x upon delta x prime is 1 by cos theta. The constraint relation between these two is this. Okay. So you can imagine now in this diagram, if that point P is actually shifted, then accordingly these two things have got stretched out, and this one has got compressed. So this one has become L1 minus delta x, and these two have become L0 plus delta x each. So this is like a one-line solution. You can see this. I've explained it in detail, but otherwise what you can do is you can just understand it from this diagram, that if this point is moving towards C with a velocity V, then the approach velocity towards C is this much. So the separation velocity from B and A is symmetrical, and it's V cos theta. So whatever displacement it has towards C, it will have a displacement away from A and B with this kind of ratio. It will be V cos theta into that time, whereas this one will be V into time. So the ratio of those displacements will come in terms of cos theta. So this is the shortcut method of applying the constraint relation. Remember, in a system where you have springs involved, you cannot use virtual power method, which is otherwise the easiest constraint relation method, because virtual power, the tension should be delivering net power of 0. But in a system where there is elasticity, the elastic forces will be doing work because the potential energy of the system will be changing. Okay, so people hope this constraint relation business is clear to all of you. Okay. Now we move on to some more examples of spring-based systems, but with other aspects of mechanics also thrown in. So for example, we can have a system where there is a rotating pulley involved. Okay. Or we later see a problem where there is even a system of pulleys, or that kind of constraint relation we have to work out. Okay. But this one I'm showing right now, this will have a rotating pulley with a given moment of inertia involved. That's also an interesting type of problem. So massless thread going around the rough surface of a heavy pulley, heavy rotating pulley. On the other side, the string is attached to a spring, which in turn is attached to the ground. Okay, so this is a rotating pulley, which has moment of inertia I and radius R. This is a block of mass m. So now the block, let's take the mass of the block to be 2.5 kg, is released from rest with the spring relaxed. Okay, but the thread is joining the spring from here onwards. Okay, so this is massless thread, but the thread is taut, so it's not loose. So it's not going to be in free fall. The moment it starts falling, the spring will come into action. Okay, so the thread is taut at t equal to 0. So given that the spring constant is, let us say, 12 newtons per centimeter, and moment of inertia is, let us say, 0.5 kg meter square, and the radius of this is 5 centimeters. Let's make it this is the moment of inertia, and this is the radius of the pulley, and g is equal to 10 meters per second square. So find the time period and the amplitude of the block's vertical SHM. So again, you have to start by understanding how the dynamics will work out. That from the equilibrium position, if the block is displaced by displacement of y or s or whatever, either upwards or downwards, its acceleration has to be opposite but proportionate in magnitude. And that proportionality will give you the value of omega square, from which you will get the time period. Whereas the initial condition will give you the amplitude. So for the initial condition, you have to follow the language of the question. Oh, sorry, I was unfortunately on mute. So Aman, this is the value that you should be getting of time period in terms of pi. Okay.
Yes, I got this.
Okay. Okay, so let's complete this problem. So basically, you'll have to just use your normal rotational dynamics concepts. So if we assume that this is right now not in equilibrium, let's just assume that the block has gone below equilibrium. So if suppose this was somewhere where the equilibrium was, okay. So this has gone by some displacement S below the equilibrium. So at this point of time, this tension is T1. The tension on this side is T2. The tension is T2. So this will be having an upward acceleration E. This will be having an angular acceleration alpha. Okay. So we have mg minus T1 is equal to ma. We have T2 minus T1 into R is equal to I alpha. We have A is equal to R alpha. And we have T2 is equal to Kx. Now we can see that at equilibrium position, what should have happened is that whatever tension is here, that would have balanced the mg. This is the equilibrium situation when the acceleration is 0. And if it is balancing, then alpha is also 0. So the tension on this side is also T naught only. So the spring, if it is having an extension of x naught, so we have T naught equal to mg equal to kx naught. This is the equilibrium state. Okay, now you compare this with this set of equations. So in this set of equations, first of all,
moving up.
No, the block may be moving down or up. It doesn't matter. Its velocity can be in either direction because it's oscillating. Got it, na? So ये अगर उसका equilibrium position है, so between somewhere above and somewhere below, it's constantly oscillating. It could be on the way up or on the way down. But the fact is, if the displacement is below equilibrium, then the acceleration should be upwards. Whereas if the position is above equilibrium, then the acceleration should be downwards. So that is why I'm assuming here that my T1 is greater than mg. Oh, sorry. So I got that wrong. It should be T1 minus mg. This is what you're asking, perhaps.
Yes, sir.
Yeah. Just make a correction in this first equation. So what we'll do is, first of all, we will solve this system of equations by doing that standard method that you know in rotation, that you first substitute alpha as A by R and then divide this equation by both sides by R. So this equation becomes what? It becomes T2 minus T1 is equal to I by R square into A. Then you compare it with the first equation, T1 minus mg is equal to ma. And you add the two, so, and T2 is of course equal to kx. So kx becomes equal, or kx minus mg becomes equal to m plus I by R square into E. Now the next thing you notice that between this diagram and this diagram, if the block has gone down by S, then the spring has got an extra stretch of how much? This will become L plus X now. No? So the difference of these two is basically how much this point has gone up, and that is the same distance by which this block has come down. So L plus X, the new position of the spring, minus L minus X naught, sorry, L plus X naught, this should be equal to the displacement of the block. So X is basically equal to X naught plus S. From the equilibrium position, whatever distance the block has come down, the spring on the other hand has stretched by that much extra. So X has become X naught plus S. So we plug that in over here. Okay, so this is like a constraint relation. So we have got K into X naught plus S minus mg. So let's say this is equation A, and this thing that we are getting is equation B now by solving this system. So there we are, we got our SHM equation. Now you compare this with equation A. So substitute kx naught as mg from equation A earlier. So you get that ks is equal to basically an effective mass kind of term, m plus I by R square, or an inertia kind of term. You can see the direction of acceleration is opposite to the direction of displacement. So d2s by dt square is minus a. So that is equal to minus of k by m plus I by R square into s. So that is our equation of SHM. So d2s by dt square is minus omega square s. So s will become some amplitude into sine omega t plus 5. And in this, omega square is k upon m plus I by R square. Okay. So just make a note up to this point. I will take it forward from here. Just give me a minute. Okay, so hope this example is also clear. So as you can see, like all concepts that you've learned in mechanics, some of them you'll have to revisit while solving the SHM type of problems. So we have got this and all. Now the next thing we need to do is find the amplitude. No? For that, this data was given to us. So we can see that it is released from rest, okay, with the spring relaxed. So at equilibrium, what is happening? At equilibrium, the spring has extension, we've seen, of x naught equal to mg by k. So that extension was how much? It was 25 newtons divided by 12. So 2 point something, whatever. So 25 by 12 centimeters. So this is the equilibrium position. Now at t equal to 0, the block is displaced, the block is released from a position such that x of the spring is 0. So if x of the spring is 0, that means the displacement s is x naught above equilibrium position. Okay, so if this is your equilibrium position, then initially the block is released from here at t equal to 0. The block is released from this displacement s naught, which is actually your 25 by 12, and initial velocity is 0. So this is where it is released from. So s naught is equal to plus 25 by 12 centimeters, and v naught is 0. So from this you can see that your amplitude will become that value, 25 by 12 centimeters, nearly 2 centimeters or something, and your phase constant will be pi by 2. So again, s as a function of time will be a cos omega t. And you can see that the spring will have a maximum this thing of 2 amplitude times the amplitude and the minimum of 0. Okay, so this is when s is equal to plus a, and this is when s is equal to minus a, because it's that much below. So this is also clear. Okay. So if this is the mean position at the positive extreme above, when s is equal to plus a, that is when the spring is having 0 extension. This is when the spring is having an extension of x naught. Okay. And at the lowest position, where s is equal to minus a, because we are taking s in the upward direction, okay, what's going to happen here is that x of the spring will become 2 times x naught, or twice of the amplitude. So this is maximum extension. Okay, this is mean position, and this is minimum extension, which is in fact 0. And as the block, does its SHM up and down, the rotating pulley will be going like this and like this, alternately clockwise and anti-clockwise. It will be doing what we call an angular harmonic motion. The angular displacement of the pulley, that also you can understand that there is a relationship between the angular displacement of the pulley and the linear displacement of the block. Just like you have A is equal to R alpha. So like that, the linear displacement of the block is R times delta theta, the angular displacement of the pulley. So you'll see that delta theta is becoming proportional to cos omega t. So the pulley does what is called, the pulley performs something called angular harmonic motion. That is, the angular displacement is a harmonic function of time. Or a sinusoidal function. So it's an angular oscillation, back and forth, to and fro, but with angular displacement, and in such a way that it's a harmonic function. So it's called an angular harmonic motion. So we'll see next time that pendulums also perform angular harmonic motion. Okay. So with this, we complete the description of SHM of spring mass systems. Okay. So next lecture, we will be moving on to more examples of angular harmonic motion, okay, of various types of pendulums. Okay. And then we'll do some mixed problem solving also. There are quite a few questions in HC Verma which are to do with various combinations of spring mass systems on inclined planes, on vertical situations, number of springs attached and all that, constraint relations, rotating pulley involved, rolling objects involved, those kind of things. Okay. So start working out all those questions, and we will keep some time for discussion of mixed problems from that type also in the next lecture. So that's it for today's session, people. Thanks for attending and wish you all the best.